postdoctoral research at the University of California, San Francisco, where he cloned the human hyaluronidase. Exactly. Genes, which are involved in fertilization, embryonic development, and cancer. As a postdoctoral research associate at Brown University, Dr. Csoka was instrumental in the identification of the gene that causes Hutchinson-Gilford progeria syndrome. Progeria syndrome, a disease with many features of accelerated aging. Progeria has since revealed important insights and clues into the mechanisms of normal aging. Now he is developing animal models of progeria. I'm having trouble with that. Okay, studying the role of nuclear lamina dysfunction. Lamina? Exactly. And exploring the nexus of stem cells, aging, and epigenetics for the treatment of age-related diseases. Dr. Csoka, I'm saying that right.
That's very good.
That's very good. Has long advocated research into aging and human lifespan extension and serves on the scientific advisory boards of the Alcor Foundation and Lifeboat Foundation. Here he is.
Thank you, Hank. Thanks for that introduction. So today I'm going to talk about aging. I'm going to talk about stem cells. I'm going to talk about epigenetics. But before I get into that, I want to talk for the first 4, 5, 6 slides. I want to discuss some philosophy. I want to talk about existence itself. I mean, I know that may sound very strange, but there is a connection between the two. So, do we have a laser pointer? No? So let's go back to the very core question. Where did we come from? What are we doing here? Because at some point we're going to have to deal with the issue of God. You know, was there a creator God or was there not? I mean, most of us don't believe that there was a creation God. Let's think about it. So if we think about existence, we are here, we know that there exists. If we believe in the principle of rationality, you cannot have existence come from non-existence. So if there was a non-existent, if there was nothing at all at the very essence of reality, if there was no reality, you wouldn't just suddenly have existence. It's an absolute impossibility. So there's always been a form of existence. The ancient Greek called it the ark. So it was the ground substance of reality. It's always been there. It's the fundamental basis of existence. So again, you cannot just have existence coming from nothing. So there's always been a form of existence. So the universe, therefore, is eternal. The universe has always existed. However, the universe is not static. We look around, we see that it's always changing. It's always morphing into something else. It's always in a state of becoming. It's changing. So let's think about that a little more, about God, existence, and complexity. Again, God is, according to the traditional Abrahamic religions, God is traditionally viewed as the pinnacle of intelligence, power, complexity, the absolute pinnacle of every conceivable form of power. But again, rationally, existence cannot begin with infinite intelligence and complexity. You can't start with an entity that is infinitely complex, infinitely intelligent. It doesn't make any sense at all. Rather, the universe evolves in complexity over time. So one way of thinking about the universe is God in potentia. So it's, at the very beginning, God existed as a form of potential. The universe was not created by God. The universe may, in fact, be creating God. And if we think about that a little more, we can conceive of the idea that the universe is converting infinite potential with zero actualization into maximum actualization. So if we look at this graph, so time is on the x-axis running along the bottom. On the y-axis on the left, we have potential. On the y-axis on the right is complexity. At the very beginning of everything, there was a form of chaos. So it was the very edge of something and nothing. Barely there, barely not there. And over time, this chaos became these are both Greek terms, chaos and the arc. The chaos formed an arc. And what I mean by that was that the chaos evolved into a form of scientific laws. So the scientific laws themselves, the laws of mathematics and physics, evolved in a non-material domain. So bear with me for a second. So what I'm proposing is that before the Big Bang there was a non-extended domain. So René Descartes formulated this idea that there was an extended and a non-extended domain. I'm proposing that the universe is bio-friendly because the laws of physics, chemistry, and biology evolved in the arc. And then at the moment of the Big Bang, this Big Bang was the acquisition of dimensionality by the arc. So what we are living in is a physical manifestation of these laws. And over billions of years since this Big Bang acquisition of dimensionality, here we are today, human beings. But we're still a long way from the full conversion of this potential into actuality. So if we look at the very far top right there, you'll see that I put God. So it makes no sense at all to put God down at the origin, at the bottom left of the graph. It doesn't make any logical sense. It makes no rational sense. But maybe God is the ultimate manifestation of this conversion of potential into actuality. And we are integral participants in this process. We are sons and daughters of the universe, and we are involved in this conversion. And perhaps it's the ultimate meaning of life, is to participate in it. So what this allows is, forgive me again for getting into this, but I think it may turn out to be relevant eventually, is this allows a potential unification of science and religion. So again, Creator God is an absolute logical impossibility. But God as the end product of the cosmic evolution is a logical possibility. So there was a philosopher called Hegel who developed this idea of resolving paradoxes through a thesis, an antithesis, and a synthesis. In the philosophy of Hegel, the thesis would be there is a God. The antithesis or the antithesis would be there is no God. The synthesis, the resolving step of this argument would be God is becoming. So the universe is becoming God. And just as an aside, this isn't really relevant to this discussion, but perhaps we are still connected to the arc, so to the non-dimensional aspect of reality, and it accounts for some so-called paranormal phenomena. So they're not really paranormal, they're not beyond nature, they're still part of nature. But there's some incredibly solid data from quantum mechanics verifying this, that there is a non-local, non-dimensional aspect to existence. And perhaps this dimensional existence that we're living in is connected to this non-dimensional realm. But I'm not going to get into that today. So, what does this mean to us as human beings again? So, there's this ancient Hermetic principle, as above, so below. And what they meant by that was, a human life is like a microcosm of the universe. We're integral to the universe. We are like holographic representations of it. And a human life is also the conversion of potential into actuality. So we start out as incredibly simple things, fertilized eggs, zygotes. We grow, we become babies. We're completely dependent on our parents. We have zero control over the environment and so on. But we convert our potential into actuality during our lives. So what would greatly extended lifespans mean to this process? It would allow the conversion of our potential into the maximum actuality. In our lives today, if we make a mistake, if we get sick, if we turn the wrong way, if we make some kind of existential error, it's all too easy to lose everything. If we can live for 1,000 years, doesn't matter, we'll fix it. You know, we'll get another chance. You know, human life is incredibly brief, it's incredibly fragile. We very, very rarely get the chance to maximize our potential. So this would fit within the grand scheme of things of perhaps the meaning of life, but how can we do it? How can we extend our lives? Which leads to the biology, like what is aging? And I'm going with one of the original researchers into evolutionary biology and aging, August Weismann, who proposed that aging and death are caused by worn out tissues. So he said this well over 100 years ago. And in one of his scientific papers, he said, death takes place because a worn out tissue cannot forever renew itself, because a capacity for increase by means of cell division is not everlasting but finite. So in other words, aging is caused by loss of cell proliferation, of cell division. And Weismann sort of argued this principle by looking at evolution. So billions of years ago on Earth, there were single-celled organisms like Pandorina marum on the left, which was a very simple, well, excuse me, not a single-celled organism. It had several cells, but all the cells that made up this organism were absolutely identical. These cells would divide, and then some of them would branch off and form another organism. So it kind of split and was, in a sense, immortal in that way. Over millions of years, Pandorina marum evolved into other types of organisms, such as Volvox minor, for example, which, for some reason, split its cells into two types. So there was the somatic cells, like, you know, we are made up of somatic cells, but also it created some cells called germline cells, and these were the cells that were immortal. These were the cells that formed the new Volvox in the next generation. And this basic pattern has been maintained all the way to us. So we still have extremely mortal cells, but we have an immortal germline. And that's what allows perpetuation of the species. So there's like a split in the proliferation potential of cells between immortal germ cells and mortal somatic cells. So this is like the basic idea, as outlined by Weismann, that you have this immortal germline substratum, and all through evolution you have these mortal disposable somatic cells, mortal generations, including ourselves. So our somatic cells are discarded, our bodies are discarded, but the germline maintains life. So life is, in a sense, already immortal. It already has that capacity, but it has not granted that immortal potential to our body cells. However, as you know, in very recent times, in the last decade or so, we've discovered ways to circumvent this process. So we can clone animals, we can reprogram cells. We can take a somatic cell, like Dolly the sheep, for example, was a mammary cell that was artificially implanted into an egg cell. And that egg, because that's part of the germline, could reprogram that somatic cell into an embryonic state. It reconnected it with that immortal germline. And we can also do that with human cells. We can reprogram cells. We can transfect genes into cells, into their nuclei, and artificially convert them back into an embryonic stem cell. So we know that in principle, this division between immortal and mortal cells is only a matter of gene expression. It's nothing more than that. So what is the fundamental principle of anti-aging technology, of regenerative medicine? So if you think of this immortal germline at the top in the green, what we want to do is transfer some of these characteristics to our mortal cells, a partial transfer of the characteristics. We don't want to convert our cells into embryonic cells. If we did that, literally, we'd just turn into a kind of amorphous blob. I mean, we don't want to be like an embryo. So we want to we want to transfer some very specific characteristics of these cells to our mortal cells. Before I get into how we can do that, I just want to talk about cell proliferation and aging again. So I agree absolutely with Weissman that human aging is a loss of cellular proliferation. But why is that idea so, why isn't that accepted? It's been around for, 50 years, maybe more, maybe 100 years, like cellular senescence causes aging, but you talk to aging researchers and they'll say, well, maybe not, maybe it's this, maybe that. I think the reason is that everyone is focusing on forms of damage, like telomere shortening, mitochondrial dysfunction, aneuploidy, abnormal chromosome number, DNA damage, changes in gene expression, but they all lead to cellular senescence. They all lead to loss of proliferation of cells. And there's like two basic outcomes of that senescence. In dividing cells, like in our skin, in liver, kidney, etc., there's a loss of proliferation, as you can see in the bottom left of these dividing cells. In the brain, in the neurons, which are not dividing, they still senesce. So there's been some recent experiments showing that neurons do senesce in a very similar way to proliferating cells. But because they're not dividing, they actually start secreting enzymes and damaging each other. So they change their morphology in a way that is senescent, but it's not actually losing proliferation. So we have all these things that are like converging on causing senescence that can be manifested in two ways: loss of proliferation or the generation of a secretory phenotype. So if we want to try and reverse this, if we want to give cells the ability to proliferate indefinitely, how can we do that? There's a term that's started to be discussed called epigenetic rejuvenation. What that means is, again, if we consider time on the x-axis, cellular time, cellular age, and then differentiation of a cell on the y-axis. If you start out, on the bottom left with an embryonic cell, as you go through differentiation, as you go through age, that cell moves to an old differentiated cell at the top right. So that happens to all of our somatic cells. This is aging. With reprogramming or cloning, what happens is we're reversing, along that line. So with reprogramming or cloning, we're going back directly, artificially, back to this embryonic cell. And as I said, we don't want to do that to treat aging. We don't want to turn into a massive embryonic stem cell. What we want to do is move along the age axis only. So we want to go from an old cell to a young cell without going back to the embryonic state. So we know that there are some genes already discovered that can partially do that, like telomerase. But we need to be looking for other genes, and they are out there. And I suggest that this should be a major focus for gerontology in the next 2 decades or so, that we find genes that allow cells to traverse this axis without going back to the embryonic state. So what does this mean if we do ever accomplish this? If we do this in the next 20 or 30 years, what could it mean? Well, there's a lot of people talking about overpopulation. Maybe it could eventually become a problem. What I suggest is that maybe we can integrate some of the knowledge coming from exobiology, from astronomy, from cosmology. There's the Fermi paradox. If life is so common in the universe, if evolution is inevitable, where are these civilizations? We know that there are trillions and trillions and trillions of exoplanets out there. We didn't know that 20 years ago. We know now that there's almost an infinity of planets in the universe. But where are these intelligent civilizations? There's no concrete evidence. So what I'm suggesting is that human civilization, our civilization, may be the first in the galaxy, if not the universe. We may be the first. So far, there's no evidence of any other life, let alone advanced life. So maybe it's our responsibility and privilege to determine the future of the universe. That's a bibliography. Thank you.